Mhm.
Now, or her seat. So the next presentation is going to be given by Panayiotis Panayotaros from IIMAS here in Mexico City. And we can see that he will tell us about surface water waves in a triangular domain. So please start.
Thank you. Well, I will talk about something, a rather recent work with Rosa Maria Vargas Magaña at the University of Bergen, for a former student, and some more recent unpublished work with Dalí Guerra and Boris Persino from the University of Chiapas. And we'll see how we do about time. Thanks the organizers for this interesting and diverse workshop. This is a bit of a change of problem, because we are interested, or I have been interested, and interested also my colleagues, to the problem of water waves in domains with inclined walls. There is this kind of inclination in the lateral boundaries. This is a fluid here, water, let's say. This is the surface, and this is a rigid wall. And it is a problem that has quite a lot of interest in coastal engineering, and there's a lot of other engineering applications, for example, in sloshing of water waves in basins. And we want to model this problem. We want simplified models and try to see how we can analyze. But all this within the framework of what is called free surface potential flow. It is a very special, we might say, case of inviscid flow, where the velocity here, we have a free surface, what I call the free surface, and the water is over here. Here is the bottom of the sea. And it is assumed that the velocity of particles in the fluid are given by a gradient of something called the hydrodynamic potential. So this is the assumption. And it is so a very special case where we have where this velocity has zero curl. So it's irrotational, what's called irrotational flow, constant density, etc. It's a very simple model. And because of these extra assumptions, or particularly incompressibility, this potential, this so-called hydrodynamic potential, is a harmonic function in the fluid domain. The fluid domain varies with time. So this is in some sense, a very standard assumption to make when you study water waves, although it's it looks very special, but has been actually used for over 2 centuries, and quite successfully. One advantage is that we can extract from the standard equations of fluid flow Euler equations something simpler, equivalent equation, where we have this eta that describes the free surface that I call the wave amplitude, assumed to be the graph of a function. There's no overturning. And also the other quantity, dynamical quantity, is the trace of this harmonic function at the free surface, I would call Xi. So we can write a PD. I will write it, I will show it in a second, for the evolution of these 2 quantities. And as you can see, if we are in 2 dimensions, as we stick to 2 dimensions for this talk, but this can be done for 3 dimensions, we have quantities that have 1 fewer spatial dimension. So this is, it's considered an advantage. It's certainly an advantage in many, from a PDE setting, we have 1 dimension less. And so these kind of assumptions have led to, have been quite successful because they're quite appropriate for lab and ocean scales, and in problems of channels. I mean, we have experimental channels that are 20 meters, but also we can study coastal processes and also in the open ocean. So, and also we can cover a wide range of length scales. And then there are also simplification based on this model. It's not appropriate for large, for motions that have a larger scale, like geophysical scales, where the Coriolis force plays an important role and needs to be coupled with vorticity. Now, what exactly, what is in this geometry that I had, I did not give details, but there's no, let's say that we're in the case where there's no boundaries, like an infinite domain, and we have equations for this wave amplitude and surface potential. And this equation was written for the first time in '94. Even the model I said is very old, from the Euler equations. There is no approximation here. Zakharov's role will be seen later, but it's not, however, explicit. I mean, it looks like it's an explicit equation, but there appears an object that is, in fact, the normal derivative as a function of this harmonic function at the surface times some factor that's explicit as a function of the boundary condition, the Dirichlet boundary condition, and the shape of this object of the water, the domain, which changes in time. So, so at each time we have to somehow approximate this object, and because we don't have an explicit domain, we have a lot of information, but we don't have a formula. So, but what has been done for a long time is to write some kind of approximation. For example, when the amplitude is small, for small amplitude, we could approximate that based on the simpler problem where this amplitude is simply 0. We have flat surface. And of course, this is easier to approximate also when there is no bottom topography. But the point is that here we see, for example, something that have been assumed and have been actually shown, but I'm not going to details, but the point is that this object can be expanded in powers, homogeneous powers of the wave amplitude, and one gets, therefore, I mean, using, for example, this truncation, we just plug it in and get one model. And that has been done for a long time, but in a much more complicated way. I mean, you don't understand what's going on. People expand in Fourier transform the linear problem, then they go back and forth. So this sort of clarifies how these models are obtained. And it's also the main dynamical quantities that are sufficient to describe the problem. Now, we want to, so we're influenced by these ideas, but we want to do something in a different geometry where we have some boundaries. So the fluid domain is not infinite. We have some, and so here I'm showing an example where the fluid is at rest, when it's at rest, when there's 0 velocity and the surface is flat, occupies a triangle that's isosceles and with 45-degree angles. And also, I'm assuming that the motion is occurring in a larger domain, which here is a quarter plane. So, so that is a very special case of what I want to do. And I'm starting with problems like that, for example, the 45-degree triangle and triangular domains, because there is some linear information, because you can think also that independently of how you model the system, there is some kind of linearization, there's some linear model linearization around the trivial state where there's no motion and some kind of nonlinear terms. That would be that would appear in any model, including other effects, viscosity, vorticity, etc. And so there has to be some analysis of a linear problem first to get starting. And in this particular problem, there was actually some work. It is sort of exact linear theory. I will explain in what sense, by Kirchhoff. And then there was some other, a little bit more of literature in the 19th century, some other angles, some special angles. So for some triangles, people have exact, let's say, the exact linear theory. And the spectrum, for example, which gives us the frequencies, the linear frequency is obtained by, the problem is reduced to some transcendental equation, and then you can solve it numerically or understand it very completely. And the eigenfunctions appear, the normal modes, in closed form expression, so out of some reason. And also there's some results of this type for 3D domains that have constant cross-section that are triangles. So more recent review. So there's not that much on all this. And also part of the motivation, I mean, this is not looking at these problems. We looked at these problems somehow. We found them by accident, not by accident, but by trying to do something a little different. What these studies do is they consider this eigenfunction problem. G actually is just a constant of gravity. I put it here. It's just a constant. But you see here that the operator is the normal derivative of the potential at the free surface. So here the free surface is at rest. So this is just the derivative vertical in the vertical direction. At the flat surface of this triangle, by surface, the free surface is this. So this phi is a harmonic function in the triangle, and also its normal derivative is 0. That's this Neumann condition is satisfied here at the ridged wall. That is a condition that there's no normal velocity here. So that comes from the physical interpretation. And so so they solve this problem. They give us these phi's that would satisfy that plus the omegas, the eigenvalue. So there was, however, Just looking at that, okay, they have the formulas, etc., but the interpretation again is not very clear. Somehow it was not mentioned, and we couldn't find where do you get. I mean, there's some linear evolution equation behind that, but that is not. It's not clear where does it come from, what system is linearized, and also it's not clear what is the free surface, because part of the linear equation is that the wave amplitude is described by, satisfies this equation, and then we get, for these particular solutions, this expression. But this function, eta, is defined, presumably, only on this interval, and so we get some graph of something, but it's not clear where the intersection between the free surface and the wall is. So the triple intersection between air, wall. So the interpretation is not clear and is not given by these theories because they are obtained basically by analogy from, this is what seems to be the case. So we wanted also to look into that. Starting to think about this, we noticed that there is a common feature of these results. Well, first of all, we have a fluid domain, which is this fluid domain, which is a triangle at rest, at least. But there's also a larger domain in the 45-degree case, the quarter plane, where the motion takes place. And we're given not just harmonic functions on the triangle, but also in this larger domain. And they also satisfy the zero-Neumann condition in this larger domain. Somehow in these examples, the harmonic function was defined on the whole plane. It doesn't have any singularities in the case of the Kirchhoff example. And it also satisfies the boundary conditions that we want in a larger domain, which is nice because that's what we think that the motion takes place in this larger domain. I mean, it could have been something different, but for these functions, it's the quarter plane. And also, the less trivial thing is that these functions, so we have this family of harmonic functions that are also eigenfunctions of this Dirichlet-Neumann operator. So when we take the normal derivative at what we call the free surface, they also satisfy this eigenvalue problem. So now you can say that at least these functions, a family of functions like that, could be produced for an arbitrary domain, let's say by taking the plane and applying conformal mapping, etc. So, but the third element, I'm not saying that this is necessarily easy. In 3 dimensions, you have to solve some Laplace equation in a larger domain, but this is certainly the most, the thing that is not trivial at all. Now, so I want to use this kind of setup, assuming also that we can have it for, I will use this setup that is present for the 45 triangle to try to derive a nonlinear model, at least in this geometry, and then we can see how far we can extend all that to other domains. In principle, they could be extended, but that's not trivial. So I return now to, and here is actually the first idea of this work, that I decide that since I had a problem with using the wave amplitude, because the wave amplitude, the fact that it's a graph, maybe it's not such a problem, but the problem is that the domain of this might change in time because the triple intersection moves. So I decided to use as dynamical variables, well, first the hydrodynamic potential that is there by the assumptions, and also another quantity that is obtained to describe the free surface that is obtained in a somewhat indirect way. That is the integral. It's the map, the time epsilon map, under the flow of a vector field of an auxiliary harmonic function applied, this time epsilon map, to the flat surface. And here's the picture, actually. I have this this segment of reference, and I apply at each time a time epsilon map. This time is not the physical time, it's just some other variable, and up to epsilon, and I map this segment. I see where this segment goes under the flow of this vector field. And I can see that this kind of description has some automatic properties that are desirable, namely that the area is conserved and these lines, which are the walls, are invariant under this flow, and so the edges continue this, the two endpoints continue to be on the rigid wall. And also, this surface, this all follows by basic existence theory of ODEs. So, and then the surface and the fact that we have the gradient of the harmonic function. But we also have that the surface cannot intersect and self-intersect and only intersects the wall at the endpoint. So it's of course a more complicated and not explicit description, but in the end, what I can do is, thinking a bit in a more engineering way, expand these two quantities that appear, the hydrodynamic potential and this auxiliary potential, in these harmonic functions that I had, at least in the 45-degree case in other examples, and try to find an equation for the evolution of these coefficients of the expansion. Here, so the question is whether we can do that, and in fact we found out that we can do it, but we are using also a certain sort of an explicit expression for the free surface that is obtained by some approximation of the flow of this vector field. And one approximation is simply Euler's law, that is, the map at time epsilon is given by that. Of course, this is up to an order epsilon square error, but I'm using it now as an alternative for the definition of the free surface. So the free surface will be given by these points. X is on the interval that defines the segment of the reference free surface at rest. And so the goal then was to obtain evolution equations for these, for the expansion coefficients using this approximation. There is a problem that the area is not conserved now, but at least for if the boundaries of this larger domain are have constant slope, then at least we have that the points at the triple interface stay at the triple interface, and then use basically Euler's equations for potential flow. So this is the exact equations, and then we use these expansions to obtain a linear, to lowest order, a linear theory, which is actually the linear theory we had, but we have added, the addition is that we have now interpretation of where the free surface intersects a rigid wall. So that is, at least it solves that interpretation problem. And so Kirchhoff's result appears now, solves the linear equations, and from his solutions, that are these harmonic functions that I started with in the larger domain, I define their trace at the constant height points, and also the normal derivative, I'm now defining it as an operator on this function. So I have a Dirichlet-Neumann operator here for this problem, and from this, so I have these explicit expressions basically that I will show you, and then the frequencies arise from some transcendental equation that can be solved to any desired accuracy. Now, these are the normal modes. What do they look like? First, the lowest frequency mode is actually very simple. It is just this linear function, and it describes motions where the free surface goes like that. It's flat, but it goes up and down. And the higher modes have a trigonometric part and an exponential part, and this exponential part is very is basically very small in the interior, but it sort of matches these cosines, these trigonometric functions at the edge. So at the boundaries, we have this correction, so to speak. And then we have some kind of wave vector that is that satisfies an equation that we can solve, as I said, that is related to the frequency by an explicit expression. I'm not putting things in detail here, but and it's not an exact, we don't have a formula for that, but we have an equation and we can show that it can be found to any precision. In fact, this is the formula of this wave vector, the relation between the frequencies, this wave vector. We see very quickly that, well, basically this term becomes quickly 1, and this frequency, these wave vectors can be computed basically by Newton's method, and we have estimates. So in some sense, we don't have the exact frequencies, but we can approximate to any accuracy if we want to study, if we're interested in that problem. And in fact, there are reasons for that. But then we get to the next order and get what was the goal, the second goal perhaps, was to obtain this nonlinear equation for the evolution of the mode amplitudes, and we have some kind of interaction coefficients that can be, they're rather messy, but can be, we have analytic and numerical expressions. In some sense, this is something we have, some extra work that has to be done, and we have been doing it periodically, trying to simplify these things. Unfortunately, there was a hope that maybe, I mean, this as is usual, have to do with triple integrals of these functions, or triple, well, depending on what kind of interaction we have, and the derivatives, but we were hoping that perhaps in these integrals only these sinusoidal parts would appear, but it doesn't seem to be. We have the edge part also plays a role, except in some high frequency regions. So at least for low frequency modes, we have to take both into account. So it's a bit of a mess. But at any rate, it can be done. And also we have a completely equivalent equation now written as a PDE, if you like that. It's equivalent, and now it's a PDE for two quantities. One is the value of this, the trace again of this auxiliary potential at the height of the reference surface elevation, and also the trace of this, here should be phi actually, of the hydrodynamic potential. So, and then we get this PD, but it's full of this Dirichlet-Neumann operator appearing for the triangular domain. The linear part is exact, and then we have this quadratic interaction term. So this can be seen as a PDE with a non-local PDE in this interval, and then we can define the free surface. This is now a definition of the free surface. I mean, we can look at this problem, but then what does it mean? Well, the free surface is here, so it's obtained by this quantity. But there is some kind of assumption for this to make sense, that the Dirichlet-Neumann operator is such as we have this kind of pointwise condition at the two edges, and that guarantees that the free surface is always sticks to the wall. So there's some kind of extra thing that we didn't have to worry about that in 45 degrees. But this equation can be interpreted for any domain in some sense. But the problem is that, of course, we don't have much information about the Dirichlet-Neumann operator. So the Dirichlet-Neumann operator, which appeared in before, appears again, and in some cases we can in this 45-degree domain we have it explicitly. Now Well, this model, I mean, people derive models like that all the time, and there are a lot of, and they're not very, you know, it's something that has to be taken with a lot of skepticism for a variety of reasons. It might be well-posedness or local well-posedness might be very problematic unless you have analytic initial conditions, etc. But and so we tried. The other thing is that the derivation. I'm not showing any details of derivation. It has, you know, it's formal. So it is somewhat analogous to Boussinesq equations, where we have the exact linear part, and then we have some quadratic nonlinearity, because we have truncated also to higher order, so higher order terms. But so we tried at least to see. So the question is whether we can see any nonlinear effects, which means expecting what we actually saw, that some blow up in finite time. We wanted to have the initial amplitudes small enough, but somehow large enough to see some interaction. And we do see, with very small mode truncations, some non-trivial interaction between the modes. For example, transfer of energy from mode 2 to 4. Here I'm using the fact that we have an invariant subspace, the even modes, and in fact simplify the problem originally. We see some effects of non-trivial modulation when we have initial amplitudes in the first modes. But again, we have to keep the amplitudes quite small, and to see to visualize how small. This is the shape of the free surface with some of these motions. But you see here that even though I said that this is the wall, even though it's 45 degrees, the vertical scale is actually very fine because we have very small amplitude. So we only we see this kind of a non-trivial evolution for a long time, but assuming small amplitudes of this type. So, but however, one quantity that one can think as an interesting quantity to check with these models is precisely the motion of this point, because this is one of the interesting objects. How does this point move? And this is something we can get, and we can even see nonlinear effects in that. There is some kind of, so this is the maximum height, and we can see that as we increase the amplitude, here there are two modes. This is the linear problem. We seem to have some asymmetry between maxima and minima. So there's some kind of possibly interesting effects, but again, with a lot of, you know, we're not very sure. Now, one question that we examined was whether we can have a Hamiltonian model, because the system, the system is not, it doesn't have an explicit Hamiltonian structure, and there is some theory. Part of the theory of water waves in this model is precisely the Hamiltonian structure. Now, here we do obtain something like that, and I'm using again the normal mode description to find some interaction. Here's a cubic Hamiltonian that gives me the quadratic type of interactions, the same as before, but it's not exactly the same equation. This is a bit of a problem. And also the Hamiltonian has these two parts, one that we can call kinetic and another potential. The potential part has an additional cubic term that I'm not putting here. So this, which is different from what we see when we have with periodic boundary conditions or vertical walls or other, or the infinite domain. So there's something a bit different here. I want to say a few things about this, and because it's some kind of an interesting point, but I will skip details, because there is in fact the Hamiltonian formulation due to Zakharov that is here used, but we're actually going to work with a Lagrangian, and I will explain in the next slide how this problem can be obtained from a Hamiltonian or a Lagrangian that involves a physically meaningful kinetic and physically meaningful potential energy. But in the Lagrangian formulation, we basically need to express or approximate Lagrangian as a functional on this quantity describing the free surface. And then I will approximate it. I mean, the free surface, I'm using already here the approximate by the Euler equation and its derivative, and then by a formal Legendre transformation obtain the Hamiltonian. And again, we need an expression now explicitly for the Dirichlet-Neumann operator. The Dirichlet-Neumann operator previously appeared at the end, but here it must be used. There is an interesting mechanical analogy with the Zakharov theory, namely the system, the water wave system, has this form, as I said, and the kinetic energy is basically something that's quadratic in velocities and has a mass matrix that depends on the position. Or you may want to interpret this as a Riemannian metric, where this mass matrix is symmetric and positive. Oops. And then we are obtaining the Hamiltonian by defining the canonical momentum that involves the inverse of this. So this is very standard. The potential is not so interesting. It depends only on the position. The point is that the analogy is that what appears here as the inverse mass is the Dirichlet-Neumann operator. In fact, this was the Zakharov Hamiltonian for the two-periodic case, where we see explicitly how the Dirichlet-Neumann operator appears as a functional applying on the free surface potential. So this is the kinetic energy, and this is the potential energy. And we have also, under some conditions, the Neumann to Dirichlet operator, and so we are basically influenced by that, but we think that it's easier to derive, start with the Lagrangian, and so I will skip that, the details, but basically we choose, we have to choose the what are our position variables or generalized coordinates, and then express the physical kinetic energy. Now I should say that this is a kinetic energy that's also physical, because this quantity is the integral of velocity squared, basically. So this is all what a physicist would expect. That's why I call them kinetic energies. It's not that the form, it's that the form, it has a form before plus this interpretation. So we have the same, therefore we can start with the same physical definitions of kinetic and potential energy, and then just express them in terms of some variables that we choose. And so, but again, as in the previous slide, there is an explicit appearance of something having to do with this Dirichlet-Neumann operator. And so we do that. So we managed to write down the everything as the kinetic energy, etc., in terms of these variables, and obtain everything explicitly. But we also have to use some expression for the Dirichlet-Neumann operator that appears in the very beginning, because this quantity will appear in the very beginning, and we have to use an approximation. Now, the approximation that we use here is a somewhat interesting point that this was proposed by Ablovitz and Haut. In order to find the map from the boundary value to the normal derivative, we use two steps. We first expand, so we have the trace of this harmonic function in the at the free surface, and we expand it in some harmonic functions, in some series of harmonic functions in that on that surface. So so we have to find the non-trivial part is to find these coefficients. It's a linear problem that we have to solve, and then we just, when we have them, we just evaluate basically these term by term, these derivatives. So we have a perturbative evaluation of this step, but it's kind of interesting because it somehow connects this solution of this elliptic problem with these functions in the larger domain. So there's a question here of what are the exact connections between these two things. But at any rate, we do obtain some expansion, as I said, solving also this linear problem in a very naive way, which we also know that is not correct for high frequencies, but at least this is what we get. And then we get, we also obtain, we notice that what we obtain is the same as what Craig and Sulem, another approach to, again, how to use these harmonic functions in the larger domain to obtain the Dirichlet-Neumann operator. They use a different way where you use the definition of the Dirichlet-Neumann operator and these functions to obtain the Dirichlet-Neumann operator. But what we do actually is this leads to the same results. We check that later. But all this, again, has to be considered very carefully because I mean, there's further work on the convergence of this series, but and there are results, as I said, on the convergence, but cutting at any power causes problems because apparently there's high frequency cancellations that are not that are missed when in the convergence result when we cut to any model. So all this has to be taken with a little bit careful. But at any rate, we wanted to do another of the goals was to compute something, and we computed a nonlinear correction to the frequency of the lowest mode, which is this sloshing mode. That can be done, and here I will essentially with normal forms, but we use the model that is not Hamiltonian here. We want to use that and find some frequency correction. It can be done for this lower mode. Again, cutting, the method of course can be, our method is applicable to any number of modes, but we wanted to have some computation again, and we found some correction to the frequency dependent on the amplitude. In other words, the frequency is the linear frequency of the first mode known and something that's depending on the amplitude of the motion. This, of course, is on a, we use changes of coordinates and all that. But as was expected, we need this. This uses some cubic interactions that are produced by the change of coordinates, but it's not consistent. Even though it might be, in some examples, it might be close to the right result, it's not consistent. We need also to compute quartic terms, which is something that we can do with our approach, but it's stretching all these ideas. So at any rate, this is just a first iteration, and there are other ideas, for example, for describing the free surface. The one I used is a little complicated. It has some advantages. There are others. But in fact, there was some criticism to what we've done, etc., that we are considering. But one idea that I want to present some these newer results is to use conformal maps to study the Dirichlet-Neumann operator, and because conformal maps can be used even to map this domain to some reference domain. So in the description of the free surface, that at least is available in 2D. It's again a complicated description. It's not the simplest, but so we want to extend these exact results to a bigger triangle and to other triangles. And as I said, the linear modes are an important part of our theory. For computing things, we have to have them, and we use them. So we want to fix the side, what we call the free surface, and vary this angle from 45 to pi over 2 to a vertical wall. So, or think having the actually this is actually the next slide. Sorry, having from 45 here, increasing it up to 90. And that, of course, the depth of this triangle is not constant, and in the limiting case, it's just it's this domain. It's an infinite domain. But so And using the fact that we have conformal map very simply by Schwarz-Christoffel transform, and the free surface, so the half plane is mapped to the triangle, and the free surface is now this interval -1 to 1. And we have explicit expressions for the Dirichlet to Neumann eigenvalue problem. We have the derivative, the Hilbert, composed with the Hilbert transformation, and then multiplication by something this map at the boundary. Of course, at the boundary, this map is known, and it's singular. Of course, the derivative is not. That is the main problem, perhaps, that this map is not conformal precisely here, and there's no way to avoid angles in this problem. So, but at any rate, we did some numerical work. We were also influenced here by some work of Fontelos and Lopez Rios, who did in a semicircular domain something similar, but we also used Chebyshev spectral and collocation methods to solve this numerically and see whether we see something. Anyway, as we move therefore so we want to move from an angle that is pi/2, slightly decrease the angle and reach 45. That's what we do for the time being. And these two cases, the two cases are, well, this is kind of trivial, and we have exact results, and this is where we have the Kirchhoff results. So there are two cases where at least we know where we should get. Now, there are basically the following observations from the numerics. The first possible conjecture is that the slope, the asymptotic slope, here I'm showing you the eigenvalues as a function of the index, the increasing, they're positive, etc. And we claim that the asymptotic slope should be a half and independent of the angle. So from here to there, all the intermediate triangles, we expect, or we conjecture that, or the numerics, we have evidence that this is, and it's 1/2. It's actually the slope that you see here. It's a slope in this area, in this region. I mean, it's actually in the high frequency, I would say somewhere here. It's not true the truncation has its own effects, but we claim that this is actually, that it's this area that captures the high frequencies slope for all the angles. So it's independent of the angle, and this 1/2 is a quantity that is only related to the length of this side, which remains constant. The second point, the second point is that it's not very clear here, but it's that for large n, we have a constant shift. We start with n/2, which is the value of the of the eigenvectors for the vertical walls. And then for large n, we have an asymptotic shift. Now, what is this shift? Let's say that we fix here, I'm showing the eigenvalues for different slopes, starting with pi/2 and going to 45. So I take, let's say, the nth, let's say the 10th or whatever eigenvalue, and I see that in this, as we go higher, they move sort of rigidly. And also, there's some kind of monotonicity, because if we look at, let's say, at the 10th, and we start to change the angle, it moves, it becomes smaller, and it reaches the exact value of 1/4. So from 0, n/2, these are integer multiples of 1/2, it goes down, but this motion is rigid. So everything moves rigidly in the high frequency domain. Everything also moves to the left towards 0 and monotonically. So there is a numerical evidence for that. I'm saying, again, there has to see things to believe it, or at least to think that it's there. And finally, so this is the effect of the angle. In some sense, this is what remains the influence of the angle of the triangle is this shift. But the difference between these eigenvalues is always independent of the angle. So, and finally, the eigenfunctions that are somehow related. The information there is less precise. Precision is a problem with all this. And I should mention that precision becomes more difficult as we move away from the vertical wall. So the effects are smaller, but the computation seems to be more precise. And so it's nice to have at the end of this interval something where again we have exact results. But we need higher truncations, and also there's a limitation of how big matrices we can take to obtain set with a finite precision computation. But at any rate, the modes seem also to have some patterns, but these are less, again, there's less, the information there is still being analyzed, but we do see that here are these functions on the computational domain, that is not in the physical domain. They are, if you ask what are these functions, well, they look like Chebyshev functions with somewhat steeper, Chebyshev polynomials with somewhat steeper slopes near the boundaries. And in fact, when the walls are vertical, the eigenfunctions are the Chebyshev functions. So this is, again, an exact result. And in the physical domain, they are, again, the limit, 1/2, the vertical angles have 0 derivative, where as we close when we close the triangle, they are non-zero, but that's much more difficult to actually say exactly what it is. I mean, this information, this pointwise information is highly problematic because you have to take into account that the transformation is singular. I mean, so, but we know what singularity it has. So whether we can get this information is still not clear. These eigenfunctions may be good in some norm, but and again, when we talk about norms, we have to take into account the weights that appear because of the change of coordinates, etc. So I think I'm going to say yes. The vertical wall limit, actually, one of the things that we used is that when we look at this operator, there's some identity of the Hilbert transform where you apply first multiplication by some factor, by this weight, and then you post-multiply by 1 over that. And that cancels basically the conformal factor. And in addition, this operator is diagonal in the Chebyshev basis. So this is very useful for numerics because in our truncations, it's not a diagonal matrix, so it's good to know what we expect there. And at any case, so this is what I have for the moment, and thank you for your attention.
Thank you very much for your presentation. So we open the discussion. Are there questions? Yeah, so let's start this.
Have you studied the no-symmetric problem?
No. Well, that's a good question because in these patterns, we don't know what will happen, but yeah, that's a very good question. It's very easy to do it, but our results are still very somewhat tentative because the precision is not. So we are moving to these things that we know better. But it's part of the question because one could ask if you have, because the point is that with a non-symmetric, you change this conformal factor and there's another exponent at the two endpoints, and the question is what happens when these two interact, whether there's even a pattern of constant shift. I mean, so a lot of this, a lot of things can change. And the other question, but this is somewhat interesting because you start to localize the problems in this and the difficulty that people had in this, in all this. It's underlying somehow the other approach that I showed. The eigenfunctions come out of some other argument that Kirchhoff had, but they're very nice functions, and you don't see any of that. So, but in reality, there is some singularity in these problems always. So, and if you have a free surface with cusps, you will have similar terms, but not in the interior. So so I think it's a nice problem, but we're moving very slowly. So.
And another question is, suppose that the angle theta oscillate about some value. Do you expect to have some kind of resonance, like parametric resonance in?
It could be tried. Well, actually, yeah, there could be effects there. I mean, yes. I mean, if all the there's something. I mean, the shift looks quite dramatic, but we have to also remember that the frequencies are the square roots of what I'm showing. So the frequencies are not shifted, all of them. That would be very dramatic for the physics, but it's the square root of these quantities that are shifted. But yeah, there could be parametric resonances, and maybe one can put a model there, but of something like that, a simple model.
Okay, other questions? That is not the case, so let's thank the speaker again. And we continue.